Hello everyone. Today we're going to be talking to you about the engineering behind a roller coaster. Now, our engineering background makes this presentation pretty interesting for us, so we hope that you guys will be interested as well. Now, in the world of roller coasters, there are two things that really matter: how high you are and how fast you're going. So for that reason, we're going to be talking to you about the Kingda Ka roller coaster, which is located in Six Flags in Jackson, New Jersey. It stands at 446 feet tall, and it reaches maximum speeds of 128 miles per hour. That makes it the tallest and fastest roller coaster in the United States. So we're going to be talking to you a little bit about the engineering that goes into making the Kingda Ka a world record holding roller coaster. I'm Abby, and I'll start us off by talking about the launch. Then Allison's going to talk about what happens during the rest of the ride. And then Zach's going to tell us how the Kingda Ka's braking system allows riders to come to a safe finish. So let's take a look at the launch. One of the things that really sets the Kingda Ka apart from other roller coasters is its lack of a traditional lift chain. Now, what a lift chain does is it drags the roller coaster really slowly up to the top. I'm sure you've all been on those. It's really kind of slow, it's not as exciting, and then it lets gravity take the train throughout the rest of the ride. But instead, the Kingda Ka's hydraulic launch system allows the coaster to accelerate to its maximum speed of 128 miles per hour in just 3.5 seconds. So let's take a look at how that happens. Now, once all the riders are in the train, all strapped in and safe and ready to go, the train's going to take its spot at the beginning of the launch track shown here. Then, according to Michael Reitz, who's a corporate engineer at Six Flags, a cable that's attached to a catch car is then wound around a giant winch. This catch car is then hooked on at the center of the train using what's called a dog clip. So then the winch is going to spin, and it's going to pull the catch cart, which accelerates the train down the track. So about 2/3 of the way down, it's going to reach that maximum speed. At this point, the dog clip is going to lift, the catch car is going to release the train. Our magnetic braking system that Zach's going to tell you about later will slow that catch car while the train continues on down the track and up over 45 stories high. This diagram explains just how this hydraulic launch system is able to accelerate the coaster. So it all starts with this pump. This is going to pump oil down into the accumulator. This is going to press on the piston, compressing the nitrogen gas that's contained in the opposite side. So then once the release valve is opened, that compressed nitrogen is going to force the oil out of the accumulator. It's going to flow through the system, powering the motor, spinning the winch, and accelerating the train down the track. These images are showing the parts that are actually used by the Kingda Ka roller coaster. So this first one depicts the accumulator where our nitrogen gas is stored. The image here, second image in the center, shows the motor powering the winch shown in the final image. And Kingda Ka's hydraulic launch system actually utilizes 8 of these 500 horsepower motors. So now that you know how it gets started, I'm going to let Allison tell us what happens during the rest of the ride.
So as Abby mentioned before, this roller coaster reaches a speeds of 128 miles per hour. And so in order to do so, we have to take a look at the conservation of energy principle, which is that all the kinetic and potential energy at the beginning of the ride is equal to that at the end of the ride. So this green dot, as you can see behind me, pictures where this ride on the roller coaster reaches 128 miles per hour, and that's all kinetic energy. At the orange dot is where we reach a place where it's half kinetic energy and half potential energy. And at the top of the ride, as you can see shown in red, is where we reach a portion of all potential energy at that height of 456 feet. Coming down the coaster, at the bottom, we reach a portion of all kinetic energy again, although our speeds will be slightly less than 128 miles per hour due to friction losses. So now there's something called a rollback system, which is in case the coaster doesn't quite reach enough speeds to make it up and over the top of that hill. In some cases, this happens because of weather. So it may be rain or wind, but for whatever reason, it didn't quite make it to the top. So what happens in this case is the coaster goes back down that initial hill, and as Zach will talk to you about the braking system that enables it to do that safely. Now, there's one condition that is very rare, and that is that the coaster actually gets stuck at the top of the hill. So it has to be a very precise set of conditions for that to happen, and people actually have to manually climb up to the top of the hill and give the coaster a push in order for it to complete the ride. So it doesn't happen very often, but it is possible. So then the steel construction is really what makes this coaster possible. So as you can see, there's a number of corkscrews as well as that tight 270-degree turn at the top. And this wouldn't be possible with a wooden roller coaster just because the steel allows for a lot more stress to be placed on it in order to make these tight curves. So now that you've learned a little bit more about both the launch and the ride, Zach's going to talk to you about how this braking system works.
Thanks, Allison. So the last major engineering innovation that had to take place for the Kingda Ka to be successful was the braking system. Unlike many conventional roller coaster systems that use a frictional braking system, the Kingda Ka uses a magnetic braking system. There are two major components to this magnetic braking system. First, there are two high-powered magnets that are attached to the train car with a little gap in the middle. This allows for the second main component, the conductive fins, to pass through. So to take you back to physics, the principle behind the magnetic braking system relies on the conductive fins passing through that gap in between the magnets, and there are what are called eddy currents that are created. These eddy currents also create a magnetic field. It is this magnetic field that helps slow the cars down. Now, there are a few main advantages to using a magnetic braking system compared to a frictional braking system. The first of which is that a magnetic braking system requires absolutely no electricity. So this is a very important point safety-wise. So just imagine yourself, you're 456 feet up in the air, and all of a sudden something happens and the ride loses electricity. That would be very scary and it would be devastating. However, because the magnetic braking system doesn't require any electricity, you would be totally safe in that situation. Second, there's absolutely no sound produced with the magnetic braking system. So many people have been to an amusement park and we've all heard that screeching that you hear at the end of a ride due to a wooden roller coaster or some other roller coaster that is coming to a halt. Well, with the magnetic braking system, there's absolutely no sound, so it improves the conditions for both the rider and the people waiting in line. And finally, there's absolutely no moving parts with a magnetic braking system, which means that maintenance costs are significantly lower. With the frictional braking system, you have a lot of moving parts which cause friction and heat to build up. And over time, this heat wears down the brakes and it causes them to be replaced at a high rate. But with the magnetic braking system, we don't have this. Now, with all the good, there does come one disadvantage. That magnetic force that we talked about a few minutes ago is directly proportional to the speed at which the train is going. So to put that in perspective, the faster that the train is traveling, the higher the power of the magnetic force and the higher the stopping power. So essentially what you could see here in the graph is that although the magnetic field can significantly decrease the speed of the train car, there comes a point where it can no longer stop the train. So we will get it extremely slow, but we can't get it to stop completely. And for this, the Kingda Ka incorporates a kicker wheel. So a kicker wheel is essentially a tire that they place beneath the track that after it goes through the magnetic braking systems, it will roll over the tire, create some friction, and it will stop the train car completely. So today we looked at the engineering innovations that were necessary in order to make the Kingda Ka successful. First, Abby talked about the hydraulic launch system that's able to accelerate a car from 0 miles per hour all the way up to 128 in less than 4 seconds. Then, Allison talked about the unique steel construction that was needed in order to allow for the corkscrews and other designs in the Kingda Ka. And finally, most importantly, we looked at how can we keep people safe? Because it's great to accelerate people to 128 miles per hour, but you need to make sure you get them safe. So we could sit up here and talk all day, but I think really what we can do is we could show a video of the experience. So I want everyone to get ready. We're going to take you on a quick trip of the Kingda Ka. Don't worry if you get sick, it's just a video. So here you can see we're approaching. The green on the track, that's the catch car. So this is what Abby was talking about in the beginning. What you'll have happen is the train car will come up, that dog clip will become attached, and you're getting ready to go. We're going to launch in a few seconds here. Right now, we have that oil being pumped down into the pistons. The nitrogen gas is building up. We're getting ready. We're going to launch pretty soon. It's going to get really quick here. And so we're getting ready to go. We're off now. The catch car is going to disengage, and we're getting ready to get up to our full kinetic energy of 128 miles per hour. As we go up, we're reaching max potential. Do we make it over? Yes, we do. So now you see the corkscrews of the steel design, and we're getting ready to reach our potential on the other side. We're only going to be about 120 miles per hour. It's almost over. We're going to go over a hump. You're going to see the fins on either side of the track, and this is the magnetic braking system that's going to allow us to slow down. Now here at the end when we pull into the station, you'll see the kicker tire, and that's what's going to bring us down to a complete stop. So I hope everyone enjoyed their ride on the Kingda Ka today. Thank you.